All right, guys. So I'm going to go ahead and just kind of run through this whole thing, explaining all of this, especially in case maybe you wanted to hear it again from the lesson the other day or you just weren't there. So here's what we've got for graphing for rational functions. Okay. Um, so first thing that you're going to do is you're going to go ahead and get everything all fully factored and then simplify everything. That's step number one. After you've done that, you're going to find your x-intercept by taking everything that you have in the simplified form and taking the numerator and setting it equal to 0. Reason that you want to do that is because, well, you want to know when does y equal 0, and if it's set equal to y, you're turning y into 0. And that gets you your x-intercepts. Vertical asymptotes, that's what we've been doing when we've been setting the denominator equal to 0. We've also been finding holes by doing that without knowing that when we've just been doing our excluded values. So all you're doing is just taking the denominator of your simplified form, setting it equal to 0, and whatever that is, that's a vertical asymptote because, well, my denominator cannot equal 0. It's undefined. Horizontal asymptotes is a little bit different. So go ahead and explain this a little bit here. So the degree of P has to be greater than the degree of Q, meaning that the numerator has a higher, larger exponent than the denominator. So like if I had x squared over x, something like that. This is greater than this one. In that case, I do not have an asymptote. So no horizontal asymptote. Okay. Now, if the degree of P is less than the degree of Q, so that means my numerator instead is smaller than my denominator. So the opposite here. If the denominator is larger, so that's going to get you a asymptote at y equals 0. For the degree of P being equal to the degree of Q, meaning that if I have like x squared over x squared, okay, those are equal. If that happens, you take everything and you get rid of the variables and you're just looking at just the leading coefficient. And keep in mind, all of these things that I'm talking about, it's all I'm looking at is the one term with the highest degree. I don't care about any of the other terms in the numerator, none of the other terms in the denominator, only the terms with the highest degree. And those are the ones that I'm looking at in this case. And so here, like I said, it's just going to be taking the coefficients, the leading coefficient of your numerator and dividing it by the leading coefficient of your denominator. So just like that, leading coefficient of the numerator divided by the leading coefficient of the denominator. So for example, if this was 3 and this was 2, these are both the same, the x squareds, then my asymptote would just be at y equals 3 halves. So that's how that works. Okay. All right. So now identifying holes is you're going to use any common factors, meaning when you're simplifying anything that you canceled out, if you have any factors that you canceled out from top and bottom, then that's going to be a hole. So you're setting that equal to 0 and solving for that value. Whatever you get, that's the x coordinate of your hole, and you're plugging that into the equation to get back the y value of the coordinate point for your hole. Okay. So let's go ahead and do it. All right, so right here, I have x minus 4 over x plus 4. So first thing that I got to do is I've got to find all of these features. I've got to find my x-intercept. This is fully simplified already. It's already factored out. Nothing can be canceled. Don't sit there and try and cancel out those x's. Don't try and cancel out those 4s. That doesn't happen. It doesn't work that way. So instead, to find my x-intercept, I'm going to take my numerator and set it equal to 0. So I have this x minus 4 and setting that equal to 0. And that's going to get me x is equal to 4. So my x-intercept is at 4. Sorry, looked at the wrong thing. 4, 0. Okay. Vertical asymptote comes from that simplified form where I go ahead and just set the denominator equal to 0. And so here would be x plus 4, set that equal to 0, and that just gets me x minus 4. So x equals negative 4. So my vertical asymptote is at x equals negative 4. Let me go ahead and draw that. So x equals -4, 1, 2, 3, 4. So it's right here. Okay. Horizontal asymptote. Now remember, that's what I was talking about up top about the degrees of everything. Let me also go ahead and mention at this point in time the mnemonic that I had mentioned in class. Okay. It's Bobo, Botan, Betsy. Okay. Let's talk about that. This Bobo, Botan, Betsy. It stands for, on this one, bigger on bottom, y equals 0 is your asymptote. Bigger on top, no asymptote. Bottom equals top, coefficients. So again, bigger on bottom, y equals 0. Bigger on top, none. Bottom equals top, coefficients. So that's what we got there for Bobo, Botan, Betsy. It's a way to just kind of remember it. So when I come down here, again, I don't care about this -4 and this +4. All I'm looking at when I'm doing horizontal asymptote is whatever variable has my highest degree. And those both have a degree of 1. So they're equal. So what is it when they're equal? Bottom equals top, coefficients. So this is going to be y equals 1. And that's because my coefficients here are 1 and 1. 1 divided by 1 is 1. Whole. I don't have any here because I didn't cancel anything out. If I canceled something out, then I would have a whole. So here, that is none. Okay, domain. In fact, let me go ahead and also draw my horizontal asymptote here at y equals 1. Okay, my domain is going to be broken up only by vertical asymptotes or wholes. And so what I'm looking at here for my domain, it's going to go from -infinity to -4 union -4 to infinity. I don't even have to look at my graph to know that. I just know that the domain of this entire function is going to only be stopped by my vertical asymptotes or wholes. As far as my range goes, same thing. It goes from bottom to top, -infinity to infinity, but it's only broken up by my horizontal asymptote or wholes. And so that would go from -infinity to 1, union 1 to infinity. Now, look at this. I've got to figure out how to graph this, though. I need to figure out where the function's going to exist. Like, is it going to look something like this? Where is it going to be? That's what I've got to figure out. So the way that you're going to figure that out is you're going to make a table in your calculator to just get some points to plug in. So let's try that. All right, so let's get this put into the calculator. I'll show you how to put it into the graphing calculator as well as into Desmos. So if I go ahead and put this equation in, it's just the basic equation. Oh, I guess I got some stuff from the other one. All right, basic equation in here. So I'm going to put my fraction in, and again, we're going into y equals, and we're just going to put in here x minus 4 over x plus 4. Remember to get that fraction thing that I've got there, you do alpha x right next to it, and that'll get it. If that doesn't work on your calculator, you can also try alpha y equals and hit enter, and that should get it for you as well. All right, so that gets me my graph right here, and I can go ahead, let me fix my window. I'm gonna hit zoom standard. So anytime it gets all weird like that and it's not where it should be, zoom standard gets you to the -10 to 10 window that you should usually have. Okay, so I see my graph right here. I can see that vertical asymptote that we found at x equals -4. I can definitely see that there. I also can see that there is a horizontal asymptote, and I see that it is not the x-axis because I can see I'm going through it. In fact, I see it looks like I'm going through right there at my x-intercept. So that's pretty handy. So I can also go ahead and do that right now here too. Let me go ahead and plot the x-intercept. I didn't even think about that. 1, 2, 3, 4, right here. So there's my x-intercept. So I know at least now, just based off of that I have part of my graph over here, even if I didn't know that I had it over here as well. So now that I've got the graph right here, what I can also do is I can hit second and go over here to graph and hit the table. And now I can just start taking these values and plugging them in. What I'm asking you to do is just to try and find at least two identifiable points on either little side of the graph. So like -3, -7, that's a great identifiable point. So I'm going to go -3, -7. 1, 2, 3, 4, 5, 6, 7. -3, -7. So that's a point. So I've now got 2 points over here on this side, and that should be sufficient, but I'm just going to do a little bit more because I see this -2, -3 right there. So -2, -3. So I can kind of see this going on right here. -1, -5/3, 0, -1. Hey, I'm going to do that. 0, -1. So you see, I'm just trying to get myself some good points to get me a good shape. That's all. All right. And then I need to find a couple more. Now, the ones that I'm looking for are going to be negative x values over here to the other side of my vertical asymptote. And see, there's that vertical asymptote right there at -4. So now I've got a couple more identifiable points. So -5, 9. So I'm going to go -5, +9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So right there. And then -6, 5. -6, 2, 3, 4, 5. And also -8, 3. 1, 2, 3. So I can see I've got that shape there. So that's how you're going to do that. I'm going to make another video to do some more examples, but also to show you how to do this in Desmos.